All right. So I think we finished last week talking. We just sort of broached the subject of thermodynamics or thermochemistry, if you will. And your lab on Thursday will be continuing on the thermodynamics, thermochemistry tip. So last week's lab, you were doing a calorimetry lab. We're going to talk about calorimetry today and what that means. Hopefully you got a pretty good experience using it. Talked to a couple of people about their experience with the lab. This week's lab, there'll be actually a lot more, real lab stuff with, measuring the mass of things and pouring things and mixing things. And that's, so it should be fun. So anyway, we're talking about thermochemistry. Basically, all we're talking about is just introducing the concept of heat into the what we already know about chemical reactions. We know that sometimes we do a chemical reaction. There go the dogs. The reaction vessel will get warm. If you put your hand on something that, like if we're dissolving sodium hydroxide, which is one of the parts of the lab this week. If you dissolve sodium hydroxide in water, you'll notice that the temperature of the water goes up. Other things, when you dissolve into water, the temperature will actually go down. I'm sure a lot of people have like twisted their ankles or something like that and put an ice pack on it. And anyone know how those actually work? You want to unmute and give me a suggestion on how those things work. So quiet out there.
Slows down the speed of the molecules moving around?
Nope. But you're sort of in the ballpark. I mean, that would be something that would cause the temperature to go down, certainly. So what happens is that would be what we would call an endothermic reaction. And we know that an exothermic reaction releases heat when it occurs. An endothermic reaction actually takes heat in from the outside, from the surroundings, and puts it into the solution. And so with a cold pack, you have water on one side of it and a solid on the other. When that solid dissolves in the water, it actually is an endothermic reaction. And so the heat from your hand or your ankle or whatever it is you hurt goes into the bag. And so it feels like the bag is cool because it's actually taking the heat from you and putting it into the reaction. So, but basically there's no such thing as cold. There's only a heat moving from one place to another. And so if heat moves from you into the reaction, it feels cold. And so that's how that works. We'll talk about that when we talk about thermochemistry today. So we're going to talk about the different kinds of energy. Heat is mainly the one we talk about, but there's also work. We know that there's two forms of energy when a reaction takes place. Energy can be transferred in the form of heat, which is the usual way we think about it, or work can be done, like in your car engine. Enthalpy is the kind of heat of a reaction that we're generally going to talk about, and that just measures the change in energy of a system at a constant pressure. Which is if you're dealing with things in solution, pressure is not really going to change very much. Or changes with solids, pressure is not going to change very much. And really, we only see a big change in pressure when we're dealing with gases. And then only if more gases are created in a reaction than were there before. If we start with a certain number of moles of gases and then convert them into the same number of moles of different gases, the pressure is not going to change. So we can talk about enthalpy as the change in heat or the change in energy for that one. You've already been introduced to calorimetry. It's just measuring the heat of a reaction. We just measure the heat coming out of a reaction, heating up the water or any other liquid around that reaction. We measure the change in temperature of that liquid, and then we calculate how much heat must have gone from the reaction into the solution. And then we're going to talk about your old friend stoichiometry. And basically what that means is we're just going to treat heat as we would a part of the reaction. If it's an endothermic reaction, we're going to treat heat as a reactant because heat is going into the reaction and then the reactants are coming out. If it's an exothermic reaction, we have our reactants, they undergo a reaction, and heat is one of the products. And so we're basically just going to be treating energy as either going in as a reactant or coming out as a product. And if we have to balance the number of atoms and the number of molecules in a reaction, we have to balance the energy too, because heat is not created, it's not destroyed, it only changes from one form to another. And so if a certain amount of heat goes in on one side, we have to see that everything balances out. And then at the end of the chapter, we'll talk about one of my favorite parts of chemistry, because it's fun to do, is Hess's law. And part of your recitation this week will be dealing with Hess's law, and I guarantee there will be questions on Hess's law on your exam. It's a favorite of all chemistry classes. And what Hess's law says is that basically you can find the amount of energy change in any reaction if you can just find a number of different reactions that add up to that reaction in the first place. Basically, it means you can break down a complex reaction into a series of steps. And if you can calculate the heat for each one of those steps, you can add them all together and figure out what the heat of the first reaction was. And it'll hopefully make more sense when I talk about it at the end. We may not get to that today, but we'll certainly get to it on Thursday. And then related to that, number 6 is what a standard enthalpy of reaction is. That means the formation of like CO2, the formation of water as a gas, the formation of water as a liquid. All of these are sort of standard reactions, and they've been calculated. And what it also means is that the standard enthalpy of reaction of an element is 0, of the most stable form of that element. Like for instance, graphite, it's just pure carbon, and it's the lowest energy state of carbon at room temperature and standard pressure. And so the standard amount of heat that's needed to create that is 0. And so we can use that in Hess's law. If we come across an element, let's say chlorine gas. Chlorine gas is the most stable form of chlorine for that element at room temperature at 1 atmosphere of pressure. And so Cl2, how much energy does it take to form that? 0. And so if we have a reaction with chlorine gas in it, we can use that information to figure out how much energy is going into the creation of chlorine, how much energy is taken in breaking it down, because we know that standard enthalpy of reaction of the most stable form of that element is 0. We'll talk more about that a little bit later. So as I mentioned, we're just talking about energy. Energy is heat, or energy is work. And thermochemistry is just that branch that deals with chemical and physical changes. Remember, a physical change would be taking liquid water and changing it to water vapor, like in your kettle with water. That would be a physical change, but heat is involved in that physical change. We know we have to add energy to get that to work. So that would be an endothermic process, changing liquid water to water vapor. And as I mentioned, when energy is transferred from one thing to another, it's either work is done or heat is done. And in the instance of a kettle, if you put the if it's one of those whistling kettles, so heat is being transferred in there into the kettle, but you're also doing some work because you're increasing the pressure inside the kettle, and that pressure is then being released as that whistle. That's actually doing some work, and we'll talk about how we could actually calculate that a little bit later as well. So when we're talking about thermochemistry and thermodynamics in general, you have to define two things. It may seem silly, but yeah, there's two things we need to think about: the system and the surroundings. The system is actually the sum of all the energies of all the particles present in that reaction. And the surroundings, everything else in the universe. So it's just a matter of breaking down what is actually in the system, because the energy is going to change in that system. And let's say if we have a reaction going on, like say we've got a beaker, we've put an acid in it, and then we've put a base in it, and so we've got a reaction going on. We have a neutralization reaction going on. So the system would be the two liquids in that beaker, and the surroundings would be the beaker and everything else around it. And so there's energy either going into that beaker, into the solutions, or there's energy coming out. And as we'll find out in our lab this week, there's energy coming out. That's an exothermic reaction when that takes place. So the energy is going from the system, which are the two solutions in the beaker, out. It's heating up the beaker, it's heating up the air, it's heating up everything surrounding it. And we measure that change in temperature with a thermometer. But the heat is going from one place to another, in this instance, from the system to the surroundings. In the heat pack example, or the cold pack example, exactly the opposite is occurring. Heat is going from the surroundings into the system. And so we need to be able to figure out which is which so we can calculate the amount of heat going from one place to another place, okay? So a change in energy of the system has to be equal and opposite to the surroundings. And you learned that when you were doing your calorimetry experiment. You notice that all of the energy that went from the piece of hot metal you were putting into the water went into the water. And so the energy that was lost by one thing was gained by the other. And when you added them together, it came out to zero, you remember? So Q, which is what we call heat, Q of the metal going down, so it was negative, was equal and opposite to Q of the water, which was going up. And when you added Q metal plus Q water, you added them together, you got zero. And that's how you were able to calculate the specific heat of the metal by calculating exactly how much heat the water increased by. And so the change of the energy of one thing has to be equal and opposite to the change in the surroundings. So just like I mentioned, if the reaction's happening in a flask, the system is just whatever's in that flask, not the flask itself, because remember, the flask can get hot if it's an exothermic reaction, or it can get cold if it's an endothermic reaction. And so the system is what's inside, and then everything else is considered the surroundings. And we can look at, this is just basically an energy diagram explaining how we measure either energy as positive or negative. And so if energy is released, on the left side, we see the initial state is above the final state. So in this case, that would be, for instance, if we had a glass of hot water, like I'm drinking a glass of tea right here, I'm doing a chemical reaction right here. So right now my tea is going down in temperature since I made it about 15 minutes ago. And so the initial energy of my teacup, inside the teacup, was high. There was energy in there, and as Kyle mentioned, the molecules were moving very quickly. That's actually how we measure temperature. It's the kinetic energy of the molecules inside the cup. Now they're going down, they're slowing down over time, and they're releasing that energy, they're losing energy to the surroundings. So we can see, so if my initial state was my teacup 15 minutes ago, and the final state is my teacup now, energy has been lost. And so the energy of the final state is less than the energy of the initial state. And so my delta E, or the change in energy, would be negative, because energy has gone into the surroundings. Now on the second side, if I then took my teacup again, and I said, I don't want to drink this cold tea anymore, I'm going to heat it up. I put it in the microwave. The microwave, of course, adds thermal energy to my teacup. I'm adding it in there. So the final state, when I take it out, it's going to be hotter than it was when I put it in. So energy has been absorbed from the surroundings. The microwave radiation going into the water molecules, it's absorbing energy. The energy is increasing. So the final state is going to be hotter at the end than it was at the beginning. And so the energy of the final state is higher. And so we would say that the change in energy is positive. So that's why when you did your calorimetry experiment, Q water was positive because the temperature went up, and Q metal was negative because the temperature went down. And then when you add them together, you should get 0. So just as the same example here, if the energy is only transferred as heat, it's fairly easy to see where the energy went. Like if I have, like on the left, I've got my cup of tea at the top, which is hot, and then it's cooling down. That's fairly straightforward to think of, well, if the temperature goes down, that must be heat. That makes sense. So Q is negative because it's going down, it's being released. On the bottom, if I have ice water, I've got a nice cool drink. I've made myself a margarita after the end of a hard day. I've got a whole bunch of ice in there. Over time, that ice is going to melt, and the ice melts because it's taking in heat from the surroundings and changing that frozen water, where the water molecules are moving very slowly, and slowly speeding them up, changing them to liquid water. So heat is then being absorbed from the surroundings, and so that Q is positive because the temperature is going up. So that part is fairly straightforward. But what happens if work is done? Now we have to think about, is work being done to the system, or is the system doing work on the surroundings? We generally think of a system doing work on the surroundings, like in our car, I'll see another dog is going down the street. So we've got we ignite octane and oxygen inside a piston, and the piston does work to move the car. But we can also do work on a system. Over on the left side, we've got the pressure being increased on the inside as a reaction takes place. So we've got we take some hydrochloric acid, and this is a common reaction. We drop a metal into it, in this case zinc, and what happens is that zinc chloride is created when the zinc dissolves in the hydrochloric acid. And so zinc chloride is one product, and the other product is hydrogen gas. And so the pressure of the hydrogen gas pushes that piston out. And so the pressure goes up inside the system, and it pushes against the pressure of the outside and changes the volume. And we'll talk about how that is PV work, or pressure volume work. So that's work done by the system. And if work's done by the system, we say that the work is defined by the small w, just like Q is heat, small q. When work's done by the system, then W is less than 0. because work has gone, or energy in the form of work has gone from the system to the surroundings. So remember, when heat goes out of the system, Q is negative. And when work is done by the system out to the surroundings, work is negative as well. On the other side, think of, on the right side, think of that as like when you, with a bicycle pump. So you are doing the work with the bicycle pump by pushing down on it. That increases the pressure inside the bicycle pump. So here, the pressure of the surroundings is higher. You're adding force, pushing that down. And so what you're doing is you're compressing the gas inside the system, and that pressure goes up. And so when that pressure goes up, that energy is absorbed as work, and energy increases. And so we say that energy has been done to the system, and W would be positive. Let me take a little break there since I've been nattering for a while. Any questions about how that works? Which is positive and which is negative? Don't all shout at once. That's fairly straightforward, I take it. You can unmute at any time. Hopefully everyone knows how to do that.
Yeah, it's clear.
Thank you. Someone knows how to. Thank you, Matthew. Anyway, okay. So here are the conventions, the sign conventions, positive, and negative. Now remember, heat is basically gets converted into two things, or energy gets converted into two things. We measure it either Q for heat and W for work. And so if both Q is positive, like we've done work on this system, and W and we've added heat to the system, then the change in energy is obviously going to be positive, because we've both added energy in the form of heat and we've done work on it. Yes, JZ.
Someone got a question. So this person's saying if surrounding to system is negative and system to surrounding is positive. Is that correct? Like,
repeat that again?
So if surrounding to system is negative and system to surrounding is positive. I think.
Oh, yes. If let me go back. So if energy goes from the surroundings into the system, that's positive. So on the right here, pressure is being put on the system so that the pressure goes up. So basically, a piston is being pushed down on the system. I'm adding work, just like the bicycle pump. I'm adding work I'm doing work to the system. In that instance, energy is going from the surroundings, me, into the system. So that's positive. On the left side, the reaction is causing the pressure to go up, and then it's pushing on a piston out to the surroundings. So the energy of the reaction is being forced out into the surroundings. In that case, work is being done to the surroundings, and so that would be negative. So if either the energy or the work goes out, it's negative. If either heat or work going in the system, that's positive. Hopefully that makes it a little clearer. Yeah, thanks for the heads up.
Mm-hmm.
So here, just basically for heat, positive just means the system goes up with heat. Basically, the temperature goes up. If it's negative, temperature goes down. It's releasing heat into the surroundings. Now, what makes it, I think, is a little trickier to understand is like work. We think of if work is a positive thing if it's being done for us. Well, of course, right? I like to have work done for me, but remember, we're thinking about what happens to the system, to the thing we're doing the work on. And so if it is doing work for me, if that energy of the reaction or whatever it is happening inside the system, if that energy comes out in the form of work, if it changes something in the environment, generally meaning change in volume or change in pressure, PV work, we'll talk about that. If the pressure or the volume of a piston comes out into the surroundings, that's energy being released into the surroundings in the form of work. So that's work being done by the system. And so we say that's negative. If we're putting work in, if we're changing the pressure by pushing down, if we're changing the pressure of the system by pushing down, changing the volume, if we're pushing down on the volume so that the pressure goes up, we're putting work into the system. And so that is positive because it's going into. So if the system gains in heat, or if the system is gaining energy from work that we're doing, that's positive, okay? So the first law, always good to start with a law. The first law, just the thermos, just basically says that what we've been talking about before, that if you add the energy of the system plus the surroundings, it's going to be zero. Basically, it's just saying that energy is conserved. And when we do a chemical reaction, basically what we're doing is we're taking the chemical energy contained in the bonds, and we're converting that to thermal energy in the form of heat, or we're changing it into work. We're changing the energy from the chemical bonds, and we're changing it into work. Before we go any further, I just wanted to sort of ask a question. You think energy comes from breaking bonds or making bonds?
Breaking bonds.
Okay, we got one vote for breaking.
I say breaking.
Mm-hmm. Okay. Anybody else? I got 2 votes for breaking. And I see the chat is lighting up.
Breaking Bad.
Everyone's saying breaking so far? Jay-Z, is that what everyone on the chat saying, breaking?
Yeah. There's actually one person that says both.
Trying to cover the bases. Okay.
That's deep.
So no one's saying it's just coming solely from forming bonds.
I'm gonna vote that one.
That one's right. So when you think about it, I mean, it doesn't make sense at first because you think, well, you know, when you're breaking bonds, that must be releasing energy. But just think about this. It takes energy to break bonds. Bonds don't just break by themselves.
Wouldn't it be the opposite? It takes energy to make a bond?
No, no. Think about this. I mean, energy, it takes energy to break a bond.
Uh-huh.
It takes energy you have to add energy to break a bond. And then when a more stable bond is formed, that energy is then released. So it's weird. I know it took me a long time to wrap my head around. But think about when you're burning wood, or you're burning, you know, petrol, or whatever it is you're burning. Basically, what you're doing is you're taking all of those carbon-hydrogen bonds, which there's not much difference between the electronegativity between carbon and hydrogen, right? So there's not a big energy difference. But there's a big energy difference between carbon and oxygen, and hydrogen and oxygen when you form CO2 and when you form H2O. Those bonds are a lot more stable. You've even got double bonds. And so you're taking fairly low energy bonds, you're breaking them, and then you're creating high energy bonds at the end. And so when you're creating those, you actually release energy. It seems like weird, like I've got high energy bonds. So like, why doesn't that take energy to make those? Think about when you make those very stable bonds, those high energy bonds. What the high energy means is that now it takes a lot more energy to break them. the carbon-hydrogen bonds that you broke when you burned something, those are fairly easy to break. So it doesn't take much energy to break those. But then you turn them into very stable bonds, carbon, oxygen, and hydrogen, oxygen bonds. Those are much, much more stable. So you've gone from a place of relative instability to stability. And that means the energy has gone down. And so the energy has then been released into the surroundings. So just try and wrap your brain around that for a minute. But we'll come back to it in a second. But yeah, that's something that takes a long time to understand. Like, it took me many years to sort of understand what the hell was going on. But if you think about it in terms of you've created more stable molecules. And so in creating more stable molecules, energy must have been lost, right? Because you've gone from something that was less stable to something that now is more stable. And so that increase in stability must mean a loss of energy. So if you think about it that way, maybe that helps you to think about it. But we'll continue on. So we're sort of familiar now that the main unit of energy is the joule in the metric system. And we used to be the calorie. And it's the quantity of energy needed to raise the temperature of 1 degree, 1 gram of water by 1 degree. So that number there should look kind of familiar. Anyone recognize that number of 4.184?
Density of water?
The density.
I mean, not the density, the
Specific heat.
There you go. It's the specific heat, exactly, because that's the amount of energy it takes to raise. That's basically the definition of the specific heat of something. It's how much energy does it take to raise 1 gram of it by 1 degree, and it's actually a calorie. That's how much energy it takes. But then, joule was defined in a completely different way as the form of energy, and so we had to, scientists and engineers and physicists and everybody else had to work around. Okay, well, everyone else in the world is using the joule for energy. We're going to have to figure out that we're going to have to use joules for this too. And so the calorie sort of went out of favor, and the joule back in. Because really, the calorie this was the only way calorie was defined as an energy. This one way. And joule defines energy for every other thing on the planet. So that's why we're now stuck with this 4.184 rather than 1, which would make our calculations a whole hell of a lot easier, right? And then one other form of unit of energy you may come across is the BTU. And that's basically for like appliances, air conditioners. Like if you buy an air conditioner, you stick in your window, it'll say it's like, 5,000 BTUs or 10,000 BTUs. It's just basically how much it can either heat or cool something over a period of time. We're not going to be using that, but if you had to, that's how much. That's 1 BTU is equivalent to a whole hell of a lot of joules.
Are we going to use like Kelvin as that one too?
Yeah, well, Kelvin is not a measure of energy. What is Kelvin a measure of?
Oh, temperature.
Temperature.
Okay. Yeah.
And we remember that heat and temperature are not the same thing. Heat is a form of energy, and temperature is a measure of how much thermal energy there is in a system. So it's basically it's a measure of what's the average amount of energy of molecules in a system, but it's not energy itself.
Okay, gotcha.
Yeah. So here's just to give you just an idea of like how much quantities we're dealing with. So 1 calorie is that many joules, and we can go down and see that we get down to like really small amounts of energy, like 1 molecule of air at the average temperature is like an incredibly small amount of energy. But if we go on the other side, one of the things that's, I don't know, I find encouraging anyway, is that the amount of energy falling on the Earth from the sun in one day, it's just a staggering amount of energy. If we could get just like 5% of that, you really wouldn't need to get it. You wouldn't need energy in any other form, basically, because it's just a huge amount of energy. It would be like the daily electrical output of Hoover Dam times a factor of 100 million. So it's a lot of energy. And so basically, if we could just harness that, we'd be doing ourselves quite well. So here's a question we can do. So it's a standard thing we talk about, because when you burn gasoline in an engine, it releases heat and it does work. So how would we figure out the total amount of energy together? So remember that the work that's being done is actually pressure volume work, and we'll talk more about that in a second. How do we actually calculate that? But the pistons get work done to them by the reaction. So when you make a CO2 and water vapor in that explosion, it pushes the piston out. It changes the volume. And so if the expanding gases do 451 joules of work, and the system releases another 325 joules of energy in the form of heat to the surroundings, what's the total change in energy? There's a couple things we need to do. We need to define the system, and we need to define the surrounding. So in this instance, the system is the reactants and the products. It's the gasoline, it's the oxygen, it's the CO2, and it's the water vapor. That's the system. And the surroundings are the pistons, which is having work done on them. It's the radiator, which is absorbing heat from that reaction, and the rest of the car, and the rest. So heat is being released by the system, right? So we know that when we burn things, heat is released. So Q is negative because the engine's warming up, and our radiator is absorbing heat and trying to cool things down. So work is also done by the system. So Q is negative because it's being released into the surroundings, and W is also negative because work is being done by the system to the surroundings. So what do we do? So here's our Q. Q is minus 325 joules. We've defined that. The work is also being done into the surroundings, so it's negative as well, 451 joules. What do? We add them together. So we get a total of 776 joules. Let me see if my pen is working here. Here we go. Yeah, so we just add them together to get our 776 joules. But then, if we want other forms of that expression, generally when we do these sort of reactions, we talk about kilocalories, because we're going to be dealing with joule is a really small amount of energy, especially when we're dealing with large amounts of things. And so generally we'll be converting joules into kilojoules. And we know that a kilojoule is 1,000 joules. A kilo of anything is 1,000 of that thing. And so the kilojoule is larger than the joule by a factor of 1,000. So here's how we do our conversion. And if we wanted to change joules to calories, you just do this conversion here. So it would be, our answer is negative, and this would be if we wanted to change it to kilocalories, same sort of thing. All right. So this sort of leads us into how one sort of reaction can have two different paths, but the total change in energy has to be equal for them. So no matter what, so if we do the same reaction in two different places, the total amount of energy change is going to be the same, even if the amount of heat released and the amount of work done are different. In the example here, we, as usual, go back to our old friend, the car engine. So we've got some octane, we've got some gasoline, some petrol. We're burning it. We're burning it with O2. We're doing a combustion reaction. On the left, we're just pouring some in an oil drum and just burning it for heat. You know, it's the apocalypse. It's the after times, and we're just like warming our hands, you know, by the oil drum with the small amount of gasoline we can scrounge. So basically, we're releasing all of that energy from that reaction as heat. We're not doing any work because basically we're not changing. We don't have a lid on that can, so we're not changing the volume. We're not changing the pressure. No work is being done. All of that energy is being released as heat. But if we burn that same amount of gasoline in our car engine, it's releasing heat, but it's doing work also. But the thing is, we can calculate, if we calculated the heat released from the oil drum and the heat released plus the work done, it should equal exactly the same thing. So this is how we calculate work done by the system. And generally, like I said before, that work done is generally either changing pressure, changing volume, or both. And it's done usually by expanding gases, just like within the car engine. That work is done by the CO2 and the H2O taking up space as gas and pushing out the piston. So the expanding gas pushes back against the atmospheric pressure, and it does what we call PV work. And we measure that as the change in pressure, the change of and the change of volume. So generally, if we keep the same pressure on, like if the atmospheric pressure is the same, and then the volume changes, it does on the right here. Here we have a piston on the left in the initial state. We do a reaction in here, and it increases the amount of gas after that reaction takes place. And so the volume goes up, and the system pushes against that piston and pushes it out. So the pressure hasn't changed. You can see the pressure here and the pressure here are exactly the same. The difference is we've increased the volume by this much. This much here is our delta V. And so if we wanted to calculate the amount of work done, we would just multiply the pressure, which hasn't changed, by change. Okay? And this is the conversion factor we use. So when we change the volume by 1 liter against the pressure of 1 atmosphere, that change in temperature is, or that change in work is this many joules, 101.3. Now again, you won't have to memorize that. You won't have to memorize the amount of joules in a calorie. You know, I'll give you all those to conversions, because remember, I don't want you to memorize things. I just want you to hopefully understand it a little bit. What I want you to understand here is that work is calculated by the pressure and the change in volume. That's the important thing to take away. And how do we convert that to energy is with this expression right here. okay? So our reaction taking place, we got our old piston cylinder example, and we've got a constant temperature. So there's no change in temperature. So basically, if there's no change in temperature, what does that say for Q? What happens to Q if there's no change in temperature? What's our change in Q?
Zero.
Sorry, what was that? If delta T is 0, what's our change in Q?
Should be 0 too.
That's right. Okay. Without a change in temperature, no thermal energy is being exchanged. There's no heat energy going in. There's no heat energy coming out because there's a change in temperature.
What Q is again?
Excuse me?
Can you clarify what Q is again?
Q is heat. So Q is heat. So heat energy. So if there's no change in temperature, if delta T equals 0, basically that means that no heat is going in, no heat is coming out. And if there's no heat going in or out, then Q has to be 0. If the temperature, if the temperature of the surroundings goes up, Q is negative. If temperature of the system goes up, Q is positive. But if the temperature doesn't change at all, then no heat is being exchanged, and we say Q is 0. So in this instance, if we want to figure out how much heat, heat we know is 0. We want to figure out how much work is being done. We take, we see that there's no change in temperature. Okay, so Q is 0. And a volume increases from 125 mils to 652 mils. So the volume goes up. So our delta V is positive. And the pressure against that piston is 988 torr. Anyone remember what torr is? Did we go over what different units of pressure? Probably we haven't done that because we haven't gotten to the gas laws yet. That's next chapter. So anyway, so we'll go over how that works. So what's our plan? So torr is just a measure of pressure. Okay, and I'll explain. So this is the external pressure on that piston. It's 988 torr, and it doesn't change. So our pressure is constant, and the initial volume and the final volume are given as 125 mils and 652 mils. So we need, so if work is P times delta V, we know what P is. It doesn't change. Figure out what delta V is. Man, whoever's drinking or whatever, you want to mute that. All right. So then we just convert P delta V into a form that we can convert over to joules. So we need to convert that to atmospheres and liters, because that's what our atmosphere liters is equal to joules. So if we need that, our conversion factor has to be atmospheres and liters. So we'll calculate the change in volume. So the final volume is larger than the initial volume. So work has been done by the system to the surroundings. So this is our change in volume. And we know that there's 1,000 milliliters in a liter. And so 521 milliliters is 1,000 times less when we convert it to liters. So there's our change in liters. So we need liters for the conversion to work. Now here's something that you haven't come across. We'll learn more about this in the next chapter. You may have heard when you're dealing with, if you heard like a weather forecast, and you say that the atmospheric pressure is so many millimeters of mercury. Has anybody heard that one? No one's familiar with that?
Is that another unit of pressure?
Yes, but that's what the weather forecasters would say for the longest time. Is maybe you guys are just too young to remember. That's basically one atmosphere of pressure will push a column of mercury 760 millimeters. That's how much an atmospheric pressure will compress a column of mercury. And so for the longest time, pressure was measured in millimeters of mercury. And we actually have one of those in the lab, one of those old school barometers that has a barometer, something that's used to measure pressure.
Oh, so it's used to measure basically anything in a vacuum system, or
Against a vacuum, right? So if you have a column of mercury against a vacuum, the atmosphere will push that up 760 millimeters into the air. And so old school barometers would have a column of mercury. And like I said, we have one of those in the lab at Skyline. And it has a column of mercury, and you can measure the pressure of the room. And it's generally around 760 millimeters in height. When the pressure goes down, you get bad weather coming in. When the pressure goes up, you generally have high atmospheric pressure or high pressure zone. The weather is usually nicer. And 1 torr is just another way of saying 1 millimeter of mercury. 1 millimeter of mercury is 1 torr. Okay, so if our pressure is given in torr or millimeters of mercury, it's the same thing. We convert to atmospheres, because remember, we need liters, we need atmospheres in order to do our conversion. Liters is fairly straightforward, and then changing to atmospheres, again, is fairly straightforward, because it's just, if 1 atmosphere is 760 torr, then that amount is just a little bit more than 1 atmosphere, 1.3 atmospheres. And we just multiply them together. So the work is atmosphere liters, 1.3 atmospheres, that many liters. Here's our number in atmosphere liters, which doesn't make much sense. Atmosphere liters, I don't know what the hell that is, but we can convert that to joules, which we do know what that is. And here's our conversion factor. Again, 101.3 joules for every atmosphere liter of work done. So that gives us finally the number of joules. So any before I go any further, any questions about how we get this particular calculation? I know there's sort of a lot to take in there, especially with the pressure. I'll just give you pressures in atmospheres until we do the gas laws. Once we do,
and that's next chapter, right?
Right. I skipped over it. Gas laws is chapter 8, but I skipped over it because we were doing so much lab work with thermochemistry. I figured, well, we might as well do thermo now, and then we'll go back and do gas laws next. But yeah, once we do gas laws, you'll be able to all these units of pressure, because basically all we're going to be talking about is pressure and volume on temperature as well. But you'll be able to convert all these different pressures into atmospheres.
Okay.
All right, so a few more minutes. So enthalpy is what we call the change in energy at a constant pressure. So if there's not a lot of change so the most common work done by chemistry, as we mentioned before, is PV work. That's generally the form of work, is creating gas from a reaction which changes the pressure or the volume of the cylinder or whatever system it's in. So that work is done against the presence of an external pressure. And generally, that pressure doesn't change. Like, you know, we're doing inside your car, it's atmospheric pressure on the outside of the car. We don't change the pressure unless you've got, like, you know, a turbocharger or something. Which, but even then, the turbocharger just works by increasing the pressure, and the air going in, and increases the amount of work done. So generally, the common that work is done by changing the pressure and the volume. And so how we define enthalpy, just basically, it's all the energy change. It's the change in heat, for Q, and it's the change in work. And so enthalpy, we give that as H. It's just what we, in chemistry, that's just what we call the amount of heat involved in a reaction. We give it the term enthalpy because we want to be able to say, we want to be able to add both the work done and the change in heat. We can add those together. So the change in the heat and the change in work is given by delta E and PV. So we can see that if the change in pressure is 0, then this term is 0. So if delta P equals 0, then delta PV equals 0 as well. So as long as I don't change the pressure being put on the system, this little part of enthalpy is none. There's no change in pressure. So delta PV, the second term, is equal to 0. So generally, if the volume doesn't change much and the pressure doesn't change, then enthalpy is the change in energy. So if we want to calculate change in energy in chemistry, we calculate enthalpy. So enthalpy basically means change in energy, except for some very rare circumstances when we're changing the pressure. Like, for instance, like I mentioned, if you have a turbocharger or a supercharger on a car, you would take into consideration those changes in pressure. And so delta PV would be different. And so you'd have to calculate those to get the enthalpy of the reaction. But in general, enthalpy is going to be a measure of the work and the energy being done onto or by the system. Any questions about that?
No.
Okay, there's one person without a question. Anyone else? Want to check anything going on in the chat?
No, not so far.
All right, everyone's either getting it or they're asleep. One or the other. All right. So as I mentioned, enthalpy, or delta H, is a change in heat of the system at constant pressure. So generally, these are the places where that is true. So if reactions don't involve gases at all, obviously the pressure is not going to change. So if we're doing a reaction, for instance, if we're adding an acid and a base, and we're doing a neutralization reaction, and that forms salt and liquid water, we haven't created any gas at all. And so we can just measure the change in heat, and that gives us our enthalpy. Just basically no work is being done. Or if we do create gas, but the total moles of gas don't change, like if we have 6 moles of gas going into as reactants, and they create 6 moles of different kind of gas, then the pressure is not going to change. Because one thing we'll learn when we do the gas laws is that 1 mole of gas takes up a certain volume of space, 22.4 liters at 1 atmosphere of pressure. And it doesn't matter what gas that is, whether it could be hydrogen gas or chlorine gas or water vapor, it doesn't matter. Because there's so much space between gas molecules. When molecules are in the gas phase, there's a huge distance between those molecules. So it really doesn't matter what those molecules are. So they all take up pretty much the same amount of space. So if we have the same number of moles of gas going in, the same amount of moles of gas going out, then we really haven't changed the volume or the pressure. And so again, we can just measure enthalpy. And for reactions where Q is much, much larger than the change in pressure, even if the moles of gas change somewhat, if the heat involved is like much, much higher, like by a factor of 100 or 1,000, then we just say, close enough. You know, I mean, chemists are not sticklers for that sort of thing. If it's just way too hard to measure, if this change, if P delta V is so small that it's very difficult to measure, we'll just say, then, you know, we'll just measure the heat. That's close enough. You know, close enough for horseshoes, hand grenades, and measuring enthalpy. Okay. So here's enthalpy so we've looked at this before. We've looked at the heat going in and heat coming out. We've defined them as exothermic and endothermic processes. But here, instead of energy, we're gonna call it enthalpy now. Okay. So here we're combusting methane. Methane is CH4. We're adding oxygen. It's an exothermic process, right? So this also will give you an indication of when we burn something, the energy comes from forming bonds. So we're breaking the bonds in methane, and we're breaking the bonds in oxygen. And then what we get at the end is carbon dioxide and water. And it's the formation of these bonds here that releases the energy. So we can see that when we do this combustion, the energy goes down. Heat comes out. And so because heat comes out, the amount of energy now is less. So there is less energy in these compounds than there is in these compounds. Because these bonds are easier to break. So if we add a spark or we add some sort of ignition, these bonds will break and energy will be released. But you can't burn CO2. You can't burn water. You can add a spark to this all day and nothing's going to happen because it takes a lot. You have to put a lot of energy to break those bonds. And so you don't get heat out of those because you've released heat when you've created those stable bonds. Now on the right side, we've got an endothermic process. Basically what we're doing is we're just melting ice. So we've got ice on the bottom and we've got liquid water on the top. Man, that's some beautiful writing. So our enthalpy is increased. We've put energy into the system. So when we calculate delta H, and generally we don't calculate H by itself, we calculate the change, or delta H, because it's hard to measure what exactly is the energy in a cup of water. It's sort of hard to measure what that is, but we can measure the energy of it when the temperature goes up, or the temperature goes down. That we can measure very easily. So by measuring that, we calculate the change. So basically, all of this thermochemistry is all going to be dealing with changes, changing from one state to another. When I move from reactants to products, when I move from a physical reaction, where I move from a gas to a liquid, or from a solid to a gas. Something's changed from one state to the other, and those changes are something we can measure. So here is a question. See if you've been paying attention. So we're going to draw an enthalpy diagram. So this is an enthalpy diagram right here. So just either one of these we would call an enthalpy diagram, where we have a beginning process, or a beginning state, an end state. Which one has more energy? And so then we would measure the change from one to the other, okay? So here is how we write those sorts of thermochemical reactions. So if energy is being released, if it's an exothermic reaction, energy is released into the surroundings, we put it as a product. Because basically that energy is being made at the same time, being created or being transferred at the same time as our product is. So here, we're combusting hydrogen gas in the presence of oxygen. So we're burning hydrogen, and we're creating liquid water as one product. And we can think of the heat being released as the other product. So we put it on the right side of the product. Our second side is that we're adding heat to liquid water to create water vapor, or H2OG, in the gas phase. In that instance, we need to add heat to liquid water to turn it into a gas. And so if we're adding heat, we actually make that a reactant, because that's something we are adding into the system to get that reaction to go. Like, if we know that if we just have a glass of water sitting there, it's not going to do anything until we either put it in the microwave or put it in the freezer, one or the other. If we want to change the temperature, or we have to do something to it. In this instance, we need to add energy to it in order to get it to turn into a gas. So that is basically our second reactant, is heat plus liquid water gives you gas. So how would we determine the sign of delta H in these two examples? So in each equation, we note whether heat is a product coming out. That would be an exothermic reaction. In an exothermic reaction, delta H is less than 0, because heat is being released from the system to the surroundings. So our change in energy is negative. Or if it's an endothermic reaction, heat is a reactant, like in number 2. We're taking heat, we're adding heat ourselves, and we're adding it to liquid water in order to get it to react, in order to do a physical reaction. So if heat is a reactant, that's an endothermic reaction. And we know now that the change in energy of an endothermic reaction is positive, because heat is going into the system. It may not feel that way sometimes, like I mentioned with a cold pack. Your hands are cold. You're figuring, well, there's no heat. Where's the heat? The heat is coming from you. Heat is being taken from you into the system. And so if the system is increasing in temperature, your hands are decreasing in temperature. And so the cold pack is actually heating up. I mean, it's cold at first, because that cold you feel is not the ice pack, that's you. That's heat being released from you into the cold pack. So an endothermic reaction, delta H, or the change in heat, is positive. And so the delta H arrow points from reactants to products, right? So if we're moving from left to right. So if we're calculating delta H, that is my phone, and I'm going to just turn that off. Be right back. I think that's my mother wondering whether we all have coronavirus yet. So when we're calculating delta H, we're always going from reactants to products. So we're calculating what happens when we go from the left to the right side. So delta H means if the products have more energy, delta H would be negative. If the reactants have more energy, delta H would be positive. Okay, so here's how we would do that. So on our first one, we can see that our hydrogen and oxygen are the reactants, and they release energy when we burn them. And here's our product on the bottom. So that would be our exothermic reaction, right? That's exothermic as we go from high energy reactants to lower energy products and releases heat. And the amount of heat that's released would be negative, because that is heat going from reactants to products, going from the system to the surroundings. And so exothermic reaction always has a delta H of less than 0. When we're adding heat in the form of, we're adding energy in the form of heat to a reaction, it's an endothermic reaction. So we start with a low energy reactant, we add heat to it, and we get a higher energy product. So if we have a higher energy product, heat must have gone into the formation of that product. And so if it's an endothermic reaction, delta H is greater than 0. So if heat goes in, delta H is positive. If heat comes out, delta H is negative. And so you'll see for the vast amount of the time, delta H is going to be negative. Because generally when you do a reaction will go from a high energy state to a low energy state. That's just the nature of the universe, right? Things tend to go from a high energy to a lower energy, more stable state. And so that generally, that energy is released as heat or work. And so delta H is usually less than 0, but not always, because sometimes we have to add heat to get a reaction to go. Any questions so far on delta H for exothermic and endothermic reactions? I see something flashing on the...
It just says, I'm blown away.
It's a lot to take in. I'm sorry. But yeah, just the concept of if you're forming stable bonds that it actually releases energy doesn't make sense at first, right? Because when we talk about bond energy, like, you know, you've learned so far that like a single bond is low energy, and then a double bond is higher, and a triple bond is really high energy. But what that means is that how much energy you need to put in to break it. And so if you need to put energy in to break it, that also means that when it was formed, energy was released. So the same amount of energy is released when you form those very stable bonds as you need to add to get them to break again. So for instance, if one of your products is nitrogen gas, that's a triple bond. The formation of a triple bond releases a lot of energy. Anyone know what gas product there is when your car bag explodes?
I know it smells bad, so.
Do you know what gas it is?
Nitrogen? Is it nitrogen?
It's nitrogen. That's right. And so it forms super quickly because a whole lot of energy is released. When you form nitrogen gas, it releases a lot of energy, and it does so quickly. And that energy is released as work. That energy is PV work, because so the pressure doesn't change in the car, but the volume of the bag does, right? So that's actually, has anyone been in an accident with the car bag went off?
Yeah.
Yeah, it's not a lot of fun. But yeah, but that happens super, super fast. And the reason it happens so fast is that that energy is released super quick, because the formation of that nitrogen triple bond releases a lot of energy and in the form of work. Yes. Question, Jay-Z.
Okay, so there's a question, but I might get it wrong, so bear with me. So this person is asking, so the transfer energy is usually from the reactant to product in both
Usually.
endothermic? Oh, in both endothermic and exothermic?
No. Energy is a product when the reaction's exothermic. So basically, we think there's two products being made in an exothermic reaction. One of the products is the chemical product, and the other one is heat, because that reaction's actually making heat. So it's making two things. It's making the product, whatever it is. In this instance, like when we're burning hydrogen in the presence of oxygen, it's making water. That's one thing. And the other thing it's making is heat. So that's an exothermic reaction, because heat is being made. It's a product. It's going from the system out into the surroundings. We can feel when we burn something, we can feel that heat because it's coming from the reaction to us. We can feel that heat. That is an exothermic reaction. That heat was in the form of chemical bonds that are being made in the reaction, and then that energy is released to us. So that is an exothermic reaction. And so since it's exothermic, delta H is less than 0, because the system now has less energy than it used to. That energy has now been given to us in the form of heat. In an endothermic reaction, nothing happens until we add heat to that reaction. So in the form, like with water as a liquid, it's just going to stay a liquid until we do something to it, until we add heat to that reaction. And so when we add heat, we've done something to the system. We've added heat to it. And so its energy at the end of it is now in the form of a gas. It has more energy now. The temperature's gone up, and those molecules now have more energy. They're moving faster than they were before. That's an endothermic reaction. We've taken heat from our surroundings and put them into the water. So that would be positive, because we've done something to the. You have to remember that the system is wherever the reaction's taking place. Neither heat's going into it because we're adding it, or heat's coming out of it because of the reaction. And if heat's coming out, it means it has less energy than it used to. And so delta H is negative. Hopefully, does that help at all? I know that I see the chat's blowing up now, so everyone's confused.
Sorry, yeah, I was just confirming. Yeah, okay, no, yeah, you answered all his question.
Well, whoever asked, you can mute and just unmute and just go ahead. Does that make sense?
Yes.
All right, cool. Yeah, we will. This isn't the only time we're going to talk about this. We'll go over it more. We'll go over it in the recitation this afternoon as well, and in the lab we'll talk a lot more about it, because we're going to be doing reactions that release heat, and we'll be able to actually add those reactions together and figure out like how much heat would come from a different reaction. So I'm just going to end up here with calorimetry, because we did this in our lab, and we know this lovely little equation by now. That's how you calculated the specific heat of your metals by figuring out Q water. Calculated that by figuring out what's my mass of water in grams, what's the specific heat of water, which we now know is 4.184 joules per gram Kelvin, and how much did the temperature of the water change. And so that gave us Q water. And so since energy lost by the system must be gained by the surroundings, whatever the change of the heat of the water is equal to negative change of the metal. And so we could measure that heat and then figure out what the heat capacity of the metal was. I think everyone probably did a fairly good job, hopefully, with that. So I'll just end here, and then we'll come back to it on Thursday. So you can see the water has pretty much the highest heat capacity of any substance in the world. I think there's only one. I think there's a form of ammonia that's a slightly higher heat capacity, but ammonia is kind of nasty to deal with. And so if we want something to absorb heat without changing much in temperature, we go to water. That's why water is used pretty much every manufacturing place in the world where you need to lower the temperature of something. You cool something. That's how your engine works. The only reason you add something to your radiator is because if it was just water in there, it would rust apart. So you just basically add something to prevent it from rusting. That's the only reason you add something to water, because water absorbs heat tremendously well. If you want to like cool down molten steel coming out of a steel plant, you dunk it in water. So because a small amount of water absorbs a tremendous amount of heat. And you can see with metals, just like metals conduct energy, conduct electricity very well, they also conduct heat very well, meaning that they warm up very, very quickly when you heat them. That's why people want copper pans in the kitchen, because if you have a copper pan, it heats up a whole lot faster than aluminum does. You can see aluminum, it basically takes 3 times as much heat to warm up an aluminum pan as it does a copper pan. And so copper will come to heat and maintain it very, very fast. Aluminum's nice and light, but it's not nearly as good for cooking as copper. And I guess if you had an unlimited amount of money, you would make gold cookware, which would heat up even faster. But you know, who wants to make a pot out of gold? Anyway, so I'm gonna stop there. And if any other questions from today? Yes, JZ.
So I got a couple questions actually, and this is off topic of the list.
No problem.
All right, so for the pre-lab number 10, is it due on?
We're not gonna have a pre-lab for 10. I'm just gonna make I'm going to post it right after recitation today. There won't be a pre-lab. We'll just have the report. It'll be worth 20, rather than having a separate pre-lab and post-lab. It'll just be the whole report, all one. Yeah.
Okay, and then number 2, about the recitation. Do we have to print out like our own like copy of it?
Nope. You can just So for instance, here's the, and a lot of people have been doing this. So here's the recitation for today. You don't need to print it out if you don't have a printer at home. Fine. You just write down the answers on a piece of loose leaf paper. Send that in. That's fine. I mean, I know what the questions are. You don't need to repeat them back to me. So yeah. In fact, I think like pretty much half the folks have just been just turning in the answers on loose leaf. That's fine.
Okay. Yeah, who owns a printer nowadays?
Exactly. Old fogies like me still want to print things because I don't like looking at the screen the whole time. So yeah, true. That's a really good point. It's like, yeah, who the hell? It's like, you might as well ask who's got a fax machine, right? So
okay, and then my last question. So about the test, I'm just curious of like when is like the next one?
Don't know. Probably about three weeks or so, I think. Somewhere around there.
Okay, thank you.
You'll definitely have I'll give you a heads up. It won't be tomorrow's the test. No.
Are we gonna have study guide?
Yes. I'll do a study guide. You're making me work so hard. But yeah.
Okay, thank you so much.
Oh yeah, and if any of you know like people in the lab, because it's going to be kind of difficult for you to do, but if you know anyone in the lab who doesn't have access, I mean, I don't know how you would find that out. And the problem is, I found that there's a substantial minority of the class who is not coming to these Zoom lectures or the recitations or the labs, and they're not sending anything in. And I think it's because they just don't have access to high-speed internet. And the problem is you can't send them an email to ask them what's going on. But so if you're aware of any of those situations, just I mean, again, I don't know how you would know because no one's leaving their house. But if you find that out, would you let me know? Because we're trying to come up with a policy to grade folks in that situation. Because obviously we can't punish them for not having internet access. I mean, we're all sort of stuck in this situation. So if you do know of a situation like that, we just bring it to my attention, please. Okay.
Yeah, this actually happened to like our group, like AD, because like we noticed like there were some people that actually didn't join the recitation lab session. Some people actually said it's because like that they're not aware, or like the teacher didn't give like a Zoom ID and Canvas basically. But she's fixing it.
Okay. Yes, I think she's fixing it now. But yeah, I mean they everyone's coming to the same. They can come to the same class as everybody else. You can all come to the same. It doesn't really matter which. I mean, we're all doing the same lab at the same time, so you can come to either one. I'll make a point of that. Yeah, thanks for bringing that up. That's a good point. They probably were. Yeah, we're waiting for a signal. Yeah. Okay. Cool. All right. If there isn't anything else, I gotta get going, and I will see most of you in about 40 minutes or so. Okay. We'll see you for the recitation.
Thank you.
All right.
Thanks,
All
Bob.
right, everyone. Stay well now.
you.
Take care of yourselves.
Yeah.
All right. Bye-bye.